Okay, this week we have another 5 problems. The theme maybe is a little bit less clear, but we'll first do the first 2 problems and then we'll talk about the other 3 problems and then maybe I don't know if we want to talk about the theme. But anyway, let's start with the first one. Um, so basically, you're given a bunch of strings in this language, doesn't really matter what language it is, and you want to know how many words or the proportion of the words in this list that have the substring AE. Okay, so, and you want to know if it's at least 40% of the words. Otherwise, if it's at least 40%, you print one of these strings. Otherwise, you print the other string. It doesn't really matter what string it is, just that it's one or the other. So really, all you have to do is read in a bunch of words, right? Read in a bunch of words one at a time. For each one you ask, does it have the string AE as a substring? And if so, count that, and then at the end of the day, you figure out what's the proportion. Now, because the numbers are so small, the problems are so small, 15 letters each word at most, all that the other things are being so small, they're basically just about any way that you do it will work. But I still want to show you sort of I guess my way of doing it. Hopefully, is even for bigger problems that you might need something a little bit. You might need to be a bit more careful. Um, it's a good practice to try to be more careful with this, even though the problem itself appears to be quite simple. Okay, so let's just quickly say a few things. I'm not going to write the complete code here. I'll show you the code. You're going to have a string. Let's call it word. So how do you read all of them in? You would do C in arrow like this, word. This will be one word because all the strings have no spaces. It's just lowercase letters. That's fine. And you can do a while loop. Okay. And this will return true if it was successful. And if you have NF file, it will be unsuccessful and then you break out. How do you know if the word contains a string substring AE? You can use the word dot find. So string has a find function. And in here, you would put in the substring that you're looking for. And it's going to return the position where it's found. Or if it's not found, there's a special position called string colon colon not position and post. So if whatever it's find returns it's not string colon colon and post, that means you found it. So then you update some count. So I don't know. Maybe you have a count called AE is AE plus plus and so on. And of course, you also have a count that remembers how many strings you have read in this loop. So maybe you have a total plus plus. So you know how many strings you have read. And then at the end, you have to figure out if AE out of total is at least 40%. Now, in this problem, unfortunately, if all you do is you write AE divided by total greater than 0.40, well, okay. Remember that these are integer values, AE and total. If you're just using integer counts, then this is basically gonna give you 0 or 1 because this is integer division. So you have to convert to double. If you want to do that, divide and then you get your 0.40. But this is actually not safe because if you have something that's exactly 40% and you do a floating point division, you may end up with some rounding errors and it might give you the wrong results if you have something that's close to 40%. Now, because the problem is so small for this problem, you're actually not going to trigger that problem. But if these numbers AE and total can be really big, can be billions of books or whatever, then when you divide and you convert it to floating point numbers, even if it's something that's exactly 40%, the round of errors might push you the wrong way. So what do we do instead? We realize that this is what we really wanted to answer, and we do our usual trick of cross multiply. So we do AE times 100 greater than or equal to 40 times total. And now there is no chance of rounding errors, and this is basically completely safe. Okay, so those are sort of just a couple of minor points, but you know, even for a problem that's supposedly simple, being careful about these things will help you in the long run, even if this problem doesn't specifically require it. There will be some other problem that you might run into in the future where if you don't do things this way, you will end up getting the wrong answer despite the problem being supposedly simple. All right. Let's look at the next problem. Minimal Fibonacci numbers, sums. So you're given a number between 1 and 1 billion. So this is still within normal 32-bit integers. You want to find the shortest sequence of Fibonacci numbers that sum to their inputs. You should output them in increasing order separated by spaces. If there's several shortest sequences, any one will be accepted. Okay, so this is actually so the Fibonacci numbers, so first of all, Fibonacci numbers are what? Well, there are 2 ones. You usually start with 2 ones, but for this problem, the fact that you have 2 ones actually doesn't matter because you only care about the 1 ones. Okay, so 1, 2, and then everything else is the sum of the previous 2. Dot, dot, dot. Okay. And you have some number that's big, I don't know, 1, 2, 3, 4, 5, and you're going to have to choose some of these numbers to write it to add up to 1, 2, 3, 4, 5. Of course, you can always do 1 plus 1 plus 1 this many times, but you want to find the shortest possible sequence. Now, this is kind of like the coin changing problem or the knapsack problem or whatever that we have been talking about the last couple of weeks. At first glance, you have a bunch of denominations, you have a bunch of things that you can use to add up to a target, and you want to minimize. So you might say, well, okay, I have this whole list, and then you generate this list of Fibonacci numbers, let's say, and then for each one, you can say either I use it or I don't. And if I use it, I can use it multiple times, and then you try to recurse and so on. The problem is that approach doesn't work because your table would have to be as big as the number that you're trying to form. And for this problem, the number is up to 10 to the 9. So you might have to get a table that is at least as big as 10 to the 9, a billion, which is too big. Okay, so the dynamic programming algorithm, in theory, if you have time and space, you can make it to work, but it's just not going to work for us because the problem is too big. So the question is, how can we do anything better? Maybe the first question is, how many Fibonacci numbers do we even need? Well, these numbers actually almost doubles every step. Not quite, because you have 34 and 55, so the next one, it's going to be 89. But most importantly, the next one, it's at least 2 times 34. And the next one here is at least 2 times 55. So it's not quite exponential. So every 2 steps, the number will double. And you know that it's basically at most 2 to the 31, 2 to the 32. let's say 2 to the 31, and you can't double that many times, right? Because if you have 2 to the 31, if you double more than 30 times, then it's already out of bounds, right? So you basically can double at most, let's say 31 times. You double every 2 steps, let's say. So you basically have at most 60 of these. It's actually about 40 something. But basically you cannot have too many of these. So what you can do is you can just generate a list of all the Fibonacci numbers. 1, 2, 3, 5, 8, etc. up to something that is just less than or equal to 10 to the 9. And then the next one, if you're about to generate the next one and it's bigger than 10 to the 9, you just stop. You don't put that in. So we can generate a list or vector of Fibonacci numbers using the standard ways of generating Fibonacci numbers. Okay? And then you keep going until this is bigger than 10 to the 9, and then you stop. Okay, now there is one thing. So if you just keep on adding the sum of the previous two to get the next one, and the next one is too big, are you going to be in trouble in that if you're using 32-bit int to store these numbers, it's up to 2 to the 31, which is about 2 billion and 2.147 billion or so, but let's just say about 2 billion. So can I take these last two numbers that are pretty big, add them, it's bigger than 10 to the 9, and also bigger than the limits of the int, and then you end up in trouble because you have overflow? And the answer is no, because this whole vectors are always full of Fibonacci numbers that are at most 10 to the 9. You take two of these things, add them together, it's at most 2 times 10 to the 9. You're still going to be within. So this number, even though it's too big, it's never going to be bigger than a 32-bit integer. Okay, again, maybe you don't even think about this while you're doing it, but you should always think about when you get to big numbers, are you going to overflow, just to make sure that you're not going to overflow. Okay, so that's the first part. You can generate these Fibonacci numbers up to a certain size. I think it's about 40 some of them, but it doesn't really matter how many. It's not too many. That's the whole point. And now you're going to take this number and you're try to write the number that they give you as a sum of Fibonacci numbers. But not only that, you're trying to make it as small, the fewest number as possible. Now, if you have Fibonacci numbers that are bigger than 1, 2, 3, 4, 5, or whatever number they give you, then of course you cannot use them. So at some point you might have Fibonacci numbers that are where this one is bigger than 1, 2, 3, 4, 5, and then this one is at most 1, 2, 3, 4, 5. So now you can actually choose, do I use it or do I not use it? Okay, we try to minimize the number of Fibonacci numbers used. And the answer, it turns out, is if you can use it, always use it. It is never a good idea to skip it in the hope that some other combination of smaller Fibonacci numbers can make up your number. And this is kind of a greedy algorithm, I guess. And why is that true? So we talked about greedy algorithm exchange argument a little bit last time. So imagine that this is the greedy solution where if you can use it because the number fits inside the number for sum that you're trying to form, you always use it. And let's say there's an optimal solution. Okay, so up to this point, doesn't matter if you're optimal or greedy solution, none of them you can use anyway. And in this case, you decide that even though you can use this one, but you don't use it. Right, whatever this Fibonacci number is. The thing is, this Fibonacci number is the sum of the previous two. So this thing here is the sum of the previous two. So by not using this, you must use at least two other ones to cover the same amount. Because the sum of previous two add up to exactly this. Well, what if you don't use either of these two? Well, then you kind of recursively say, well, if you don't use this one, now you have to use these two to mix it up, to make up the one that you don't use, and so on. And in this case, you can show that by skipping the largest one that you can use, you will always end up using more. And the reason why this works and not in general, for the coin changing or knapsack problem, the reason that works here, it's because of the fact that each number here is always the sum of the previous two. Okay, in the general case, you might have numbers that are not the sum of anything to the two previous or three previous or whatever. There might even be some number that might not be the sum of any subsets of previous values. And so in those cases, you cannot make the same argument. But in this case, turns out that we can make this argument. So all you have to do is actually just use the biggest one you can, and then just repeat. Oops. So the code first start with getting the Fibonacci numbers. So I have a vector of integers called fib. I push back 1 and 2, and I just keep doing. Next is just the last one plus the second last one. If the next it's bigger than 1 billion, so if in the new C++, I believe C++ 17 and after, you can use these single quotes inside numbers, and the compiler basically ignores them. And basically it helps me, figure out how many zeros I typed, and so I don't have to count and then make a mistake. So if the next Fibonacci number I just computed is bigger than 1 billion, I get out the loop. Otherwise, I push it into the vector. So here, I'm building all the Fibonacci numbers that are at most 1 billion. Then I read in my target. I have an answer vector that I build, which are the numbers that I'm selecting, I guess. The number that the Fibonacci numbers I'm using. And then I'm basically going through my list of Fibonacci numbers, but going backwards because I'm going through the biggest to smallest. And for each Fibonacci number I, if it's less than or equal to n, I use it, so I update n by subtracting it, and then I push it back to the answer. I would be considering these things from largest to smallest, but I'm supposed to print it from biggest to smallest to biggest, so I reverse it and I print it. Now I'm using a while loop here. Why? Because maybe I need to use a certain Fibonacci number more than once, right? Maybe I need to say 5 plus 5 or something like that. Well, actually, it turns out that this is not possible. The way the Fibonacci numbers are, you only ever need to use at most once because of the sort of almost doubling property. So I will just take this summation and I will just change it to an if statement instead to show you that actually you only need to do it once. But if you're not sure, if you don't know the math and so on, and then don't want to think about it, you can just use while. In fact, in the back of my mind, I knew that you don't need the while, and I know that if I wanted to sit down and prove it, I could prove that you only need one of each Fibonacci number. But while I was writing, I didn't really want to think about it. And I know that it was perfectly safe to put a while loop, even if it only executed once. So I just did that, and that's just fine. Okay. Okay, so next problem is this good morning. So you have a microwave keyboard, 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. And you are trying to target a certain time, 1 to 200. And for each test case, you want to output a number that's closest to K that can be entered on the keyboard. And the restriction is you start somewhere, wherever you start doesn't matter, but the next key that you press can only go down or to the right. You cannot go back left, nor can you move your hand up, though you can press the same key again. Okay, so if you are trying to press buttons and you want to press the button, whichever one you started off, you can keep pressing that button, but as soon as you move, you can only move to a button that's to the left or below or both. Okay. So here, for example, 3 cases. If you want 180, it turns out you can just press 180, 180. If you want 83, you can press 8, but you can't press 3 because it goes back up. So the closest one is 80, apparently. But maybe you can also, do 79, for example. If it's 132, 132, that goes backwards to go to this 32, but you can do 133. So the question is, yeah, given this, given the number that the target that you're trying to do, what is the closest number that we're gonna do that we can get? Okay, so a microwave it's like this, and you have some target T. Now the T, it's not very big, it's up to 200, or K, I guess they call it. So the target K, it's up to 200, so it's not very big. Up less than or less than equal to, it doesn't really matter. Less than or equal to. Okay. So whatever K is, your best bet is to try to press exactly K. Right? How do you know if you can press it? Well, you basically just trace it, right? So if they tell you, I don't know, 180, you start from 1, so it starts here. 8, if you know the row and column, so let's say row is 0, 1, 2, 3, and column is 0, 1, 2, let's say. Then if you know that 1, it's at 0, 0, 8, it's at 2, 1, then you can see that the row increase and the column increase. If any one of them decrease, then that doesn't work, right? And then 0 is 3, 1. So the row increase and the column stays the same, so that's okay. You know that you cannot do, I don't know, 181 because 8 is 2, 1 and 1 is 0, 0. And this is a decrease in row number. And of course, it's also a decrease in column number, but either one of the coordinates, if it decreases, is bad. So why am I telling you this? Because if somebody tells you a certain sequence that they want to press, you should be able to check whether that sequence is valid. But the problem is we don't know what is other than the fact that, this is a target you want to hit. If the target that you want to hit is valid, then you're done. But what if it's not, right? If they give you, I don't know, 86, right? That's not valid. So what do we do? What we do in this case is, well, we know this doesn't work. So what's the next best answer? It's things that are one apart, one step away, 185 or 187, right? Whichever one. How do I know which one? Well, if I have a routine that will check a certain number is good or bad, I just try them both. If it works, these are guaranteed to be the best answers. If it doesn't work, now you try things that are two steps away. If any one of them works, now you know that this is the best answer because you already know that the things that are 0 and 1 steps away don't work. If they don't work, then you try the things that are 3 steps away and 4 steps away and so on. And you don't have to go very far because you know that every number is at most 200. So 200 is guaranteed to be one of the best answers. You know that the answer is no bigger than 200 because no matter what number they give you, 200 will work. So you don't actually have to try that many of them. Just try them all and see which one is closest. Of course, which one that works. So basically, you have two different portions. One step is write a function that will take a number, a time, and tell you true or false. Is it valid or not? And then the other thing is just to try. You can try it in different ways, but basically try all the times. Well, I say all, but all the ones that you care about, and find the closest one that works. And this is a classic guess and check kind of problem solving paradigm. We figure out a way to check if somebody gives me an answer, is it a good answer or not? And then there's some way of guessing what the answer is. Now we can't actually write a program to guess anything. So when it says guess, what it really means is search somehow. You can just try everything from 1 to 200 and see which one works and which one is closest at the time that you're given. Or you can go through it in the way that I said at the beginning, start from the time that you're given, and then go look at 1 apart, 2 apart, 3 apart, and so on. Either way will work. So as long as you know how to write this check, then it's not so bad. So now the next question, I guess, is how do you write this check? Right? So I kind of already show you that if you know the row and column numbers of each digit, then all you have to do is to make sure that when you go from one digit to the next one, you don't decrease in either row or column index. So how do you get these numbers, 2, 1, and so on? You can decide, for example, to write a function that does some computation, right? And maybe you can say if it's between 1 and 3, it row is 0, and then maybe you can work out some arithmetic, remainder divide by 3 or something to figure out whether it's 0, 1, and 2, etc., etc. Or I can just hard code it in. I can just say maybe a row like this, and I'll just say 3, 0, 0, 0, 1, 1, 1, 2, 2, 2. What's going on here? These are the row. If this is an array, I can just look up the row for the corresponding digits. I can just look up the row of digit 0, and that's 3. Digit 1, 2, and 3 are what? Zeros and so on. So if you do it this way, you don't have to worry about uh, doing any kind of arithmetic to figure out what is the row and column index. You just hard code it in. And you might think, oh, maybe this is not the most elegant solution, but actually this is the easiest, and perhaps some people actually would say that this is the most elegant solution because uh, you don't have to fool around with formulas and have a possibility of messing up. Let me just check I need to check my sound setting. Where's my sound setting? Is my microphone correct? Input. Okay. Actually, now I hope it sounds better. I don't know what it was doing before. Hopefully, let me just check my setting one more time. Headset. Output should source. Okay. Output is also headset. Let me just quickly. Okay, I can hear it on my headset. Okay, hopefully that whatever I recorded before, it was using my other microphone, which is not so great, but this now it's better. Okay, so if you look at my code, so let me show you. Here, so we're reading the number of cases, and wow, this just basically goes to the solve, which works on each case one at a time. And then the target I read in the K, and then I have this D, which is how far away from the target that I want. And I'm trying K plus D and K minus D. Again, I have this function called valid, which tells me if it's a valid time that I can enter. I have the row and column array that I talked about. And then if you give me a time, so if it's 0, I can always do it. If it's negative, I can't do it. Why can it be negative? Because here, K minus D, when I'm just, if somebody tell me to enter the number 10, and well, I guess number 10, you can do it. But let's say that you try something that's 11 steps away, then K minus 10, sorry, 10 minus 11 would be negative. And I don't want to count that, so that's why I check for that here. Now, I am going to, okay, so now one of the things that is a little bit unusual in this code is if somebody give me 180, the problem says that I need to start tracing from the top and make sure that I only go down and left to the right. Okay, like this. But if this is the number, this is an actual number, integer, how do I pick apart the 3 digits? Now, there are different ways you can do this. You can print it to a string, I guess, and then pick it apart. Or you can just repeatedly divide by 10. No, not like this. Wow, K is greater than 0. So let's say you have something like this. Then the next digit, it's K divided by 10 and take the remainder. So that's 3. And you process that digit. You process digit. Process digit. And now you do K divided by 10 and round it down because it's an integer division, and that will drop this. And now you'll be 18. And the next time you'll grab the 8, and then the last time you'll grab the 1, and then there'll be nothing left because K is 0.
It's easy to pick apart a number in this way, one digit at a time, from the right to the left. And so instead of checking my numbers, 180, let's say 180, 1, 5, 6, 7, 8, 9, 0. Instead of going down from 180, I'm actually going to move backwards and make sure that I'm only going up and to the left. Okay? It's equivalent, but it's a little bit strange. And I started off by saying that I'm in row 4, column 4, so that whatever this last digit is, it will always be okay. The first digit, the last digit I pick would always be okay. So here I start with the current row and column being 4. While k is greater than 0, the next digit is k mod 10. Divide by 10 to prepare for the next one. And then this checks if the next digit it's less than or equal to the current row, and the column is also less than or equal to, but that's the okay condition because I'm moving up or I'm moving to the left. I'm never moving right or moving down. So that's a good condition, but I put a not in front of it. So if that's not true, then I return false. I found a problem right away, so I can return. Otherwise, I'm okay, so I update the current row and column to the digit that I just entered. If I go through the entire thing and I haven't found the problem, then I return true. Okay, so this is basically what we call a check and guess, guess and test, or exhaustive search. You try all the different answers, pick the best one that works. And that one of the essential thing is, of course, that if somebody gave you an answer, you have to be able to write something that will quickly decide, is this a good answer or a bad answer? Okay. Let me just make sure. Okay, yeah, everything is using the right thing. Okay, so the next one, you basically have up to 12 colors. You're trying to arrange them. All the colors are distinct. You want to arrange them, but you don't want to have any bad pairs that are adjacent to each other. Okay. So basically, we're asking for permutations of n things so that no adjacent pairs come from this list of bad colors. So try all permutations. The problem is, because n is 12, if you just try all permutations, that's 12 factorial, and that's too much. If n is 10, you could just try all permutations. And in C++, there's a function called next permutation that some of you may know, and you can just use it to loop through all the n factorial permutations. Of course, it takes n factorial time because there are that many of them to go through. So for 12 factorial, it's not going to work. So what we do instead is to look for a recursive way of generating permutations. So we have in general n colors. And we're going to start by saying, well, what goes in here? Well, what goes in here? You have n colors, so you're going to try color 1, 2, 3, all the way up to n, right? So if you want to generate permutation at, let's call it the start of the array that you want to fill in. So you're going to fill in this starting position. So you have some, I guess in this case, it's a string. You can use string, you can use integer with integer numbers or whatever, it doesn't really matter. Let's just say this is my permutation A with numbers from 1 to n, let's say. And then so where then also how many the size of this array you need to know. And we're going to assume that this array originally have numbers 1, 2, 3 up to n, or 0 to n minus whatever. You put in n different things in there at the beginning. Okay, so what you do is you say, for I from start, I less than n, I plus plus. We're going to try look at all of these elements and put each one of them in turn into this position. Try all of them. They are all possible things. So we're going to swap A start with AI. So we'll try each one of these items into this position in turn. And once we fix this item, we're going to recursively call gen permutation with one more position picked. So let's say you have, I don't know, 1, 2, 3, 4, 5, and they decide to put 4 in here. So you put 4 in here. Now you put 1 here and the rest of this array. Then you recursively generate all the permutations of this subarray. And that basically is all the permutations that starts with a 4. When it's done, then you swap back the 4 into the correct place so you can try the next one. You try putting in 5 and 6 and so on. And that's how you generate all permutation. And then the base case is when start, it's at the end. So start, it's equals to n, and whatever your array is contains one particular permutation. So do something with A, whatever it is your problem requires, as a permutation, and then return from this function. And this would generate all the n factorial permutations, which again is not what we want, because when n is 12, this is too slow. But remember, the way that we do this is we put a color, we put something here, and then the next recursively we put something here, recursively put something here. What if you already put a 4 here, and you decide the next time you put a 2, and 4 and 2 are bad? Well, if that's the case, there is no point in generating any more permutation recursively, because anything that you generate from this point on will be bad. So what do you do here is that this recursive call, you would have a check. If the color A start and A start minus 1 are bad, so they're a bad pair. So if they are not bad, then recurse. Otherwise, don't recurse. Right? So if they're already bad, there's no point doing it. You can prune, you can cut off this recursion. And that's how you can make it go faster by not generating the ones that are not valid. Okay. You do have to be a little bit careful here, because if start is exactly 0, if you try to look at start minus 1, it's going to crash. So what you should do is you should say start equal to 0, 0, or this. Because if it's start equal to 0, 0, then it's all the first color is always good. Otherwise, then you check. If it's not the first one, you need to check if the previous one conflicts with the current one. Now, the problem also says that there could be multiple things, that multiple permutations that worked, and if so, there's a preference on which one you want to use. You want to use the first one that in the list if you can, and so on. So, for example, if 1, 2, 3 works and 3, 1, 2 works, you want to use this one because this one, the first position is smaller. Or if you have something like, I don't know, 3, 1, 4, 2, 5, and 3, 1, 5, 2, 4. But if both of these works, then this one is preferred because the first place that differs, this one is smaller. And basically, this is what is called lexicographical. I can spell lexical. Graphical ordering. And so what you can do is that you can, and every time you find a permutation that works, you remember it as the best one. And if you already have something that's best, you compare it and see if what you generated, it's lexicographically smaller than what you have stored in the past. And you can do that by calling the lexicographic compare function in C++. So I'll just show you my code here. Okay, so I read in N. C is C. What is C? C is a vector of strings, the colors. So I read in the colors. I have this Boolean bad array. So I remember the colors 1, 2, 3, 0, 1, 2 up, 0, 1, 2 up to n minus 1. And I have a Boolean array, bad ij. It's true if that pair cannot go together. So basically, you read in these two strings in the pair, so the M pairs, read in the two names. This is linear search in my list of words to figure out the index. So if you give me yellow, I have to figure out this is the third one on the list, or number 2 on the list, or whatever. That's the linear search, and then I just mark it to be bad. Then I have my permutation array. IOTA, it's a C++ STL function that just initialize an array or container, starting at 0, and then every element is one more than the previous one. So this will initialize as 0, 1, 2, 3 up to n minus 1. I'm not quite sure what this first. Oh, first is just to remember that I have not found anything yet. Then this search, it's kind of like what I wrote. So the array, there's a start, there's no n because n was global. So that's why I don't pass it. So if you reach the base case, if it's the first time you find anything, or lexicographical compare, the one that I just found, compared to the one that I already saved. If it's true, that means the first one in the parameter, first thing you compare is less than the other one. So it's smaller. So you want to keep the smaller one. So I copy it into first perm. So first perm is what I am actually remembering. And then first is equals to false. So it's no longer the. So basically first just means that don't compare to this before I have at least stored something in there initially. Turn 1. Why do I have this return true or false? I don't even know. Oh, because for some reason I want to count how many ways I can do something. But actually that's not used anywhere. Oh, is it? COO guys, so maybe the answer actually requires how many different ways I can make this arrangement. Sorry. So okay, yeah. So that's why I return an int. I found one way, and then recursively, whatever ways it finds, I just add it to my answer. So other than that, the rest of the code looks basically what I said, right? Good is either if I'm index is the first one, or if the current one that I just got and the previous one, it's not bad. Okay, again, this code is on my GitHub. So if you go to my GitHub, Howard Cheng /contest/caddis, you can find my code, so you can refer to that if you wish. Okay, the last problem. Oh, by the way, what was this? I said there's some kind of theme. So what is the theme? The theme is again search, right? The answer is the permutation, but this time instead of generating all permutation and checking at the end, I am generating as I go and cutting off the generation as soon as I know that it's not good. Because in this case, I cannot afford to go all the way to the end because n vector is too big in this case. Okay, the last one, it's a little bit different. You are given up to 10 prime numbers. Each number is at most 10,000. You're told that they're prime. You don't have to check that. And then you're also given two numbers, x and y, between 1 and 2 to the 31. And you are asked to print all the numbers from x to y inclusive that when you factor them, you will only see these primes and no other primes. Okay, so for example, if they give you just 3 primes, 2, 3, and 5, then 30 is 2 times 3 times 5. So that's good. 60 is 2 squared times 3 times 5. So that's good. You don't need all of these primes. So for example, 125, it's 5 cubed. 2 and 3 don't appear, but that's still okay. What's not okay is, let me think here. What's not okay? Let's say 210, right? 210 is 2 times 3 times 5 times 7. You're not allowed to have 7 if it's not given in this list. Okay, so basically what you're looking for in this case is 2 to the some exponent where these are numbers 0, 1, 2, 3, and so on. And you want these numbers to be between x and y, whatever x and y they give you, right? So x and y are between 1 and 2 to the 1 and 2, 1 billion or something, right? Something like that. Oh, 2 to the 31, sorry. Okay, fine, 2 to the 31. Less than 2 to the 31. Okay, so basically a normal int. Now, how many exponents can that be, right? How big can these exponents be? Well, if the numbers is at most 2 to the 31 and the prime is at least 2, this exponents cannot be more than 31. In fact, the total number of all the EIs sub-adding, E1 plus E2 plus E3, has to be less than 31. Because if it's more than 31, then it's guaranteed the number that you get is bigger than 2 to the 31 for sure. So what you do is you basically try all possible exponents, whatever the number of exponents you have, try all of them so that it adds up, so that when you multiply, it's still less than the x and y 2 to the 31 they gave you. Now in this case, because things are really close to 2 to the 31 minus 1, the upper limit, and each of these primes can be at most 10,000. If you take a number that's close to the boundary and multiply by 10,000, then for sure it's going to be over a 32-bit integer. So I would say that you should use 64-bit integers to store things. So basically now, with this discussion, they give you n primes. You are supposed to come up with E1 n exponents so that P1 E1 ... Pn En, it's between x and y. And you know that there are not too many of them. So what do? You can do a recursion, right? So this exponent vectors, you have n positions, one for each exponent. So what goes in here? It can go 0. Remember, 0 is a possible exponent. 0, 1, 2, 3, whatever, right? When do you stop? You stop when p1 raised to the power e1 is greater than y, right? So this, it's basically, it's not going to be that much because this can be at most 20 or something like that, or 30. Now what? Let's say that this is, the first prime is 2 and you decide to choose 5. So 2 to the 5. So that means that you have 32 now. 2 to the 5 is 32, right? Now you recursively say, well, what about the next prime? Do I use 0, 1, 2, and so on? And you can do that as long as, because you already picked 2 to the 5, as long as 2 to the 5 times p2 e2, it's less than or equal to y, right? And you keep going. So for each one, you recur. So for each one, you make a choice, and then recurse. Make a choice and recurse. And when at the end of this, you now have a vector of exponents that is a number less than or equal to y. So we check this part. And now you have to check that it's at least x. And if it is, then you add that to the list. And then you can collect that and you can print it out at the end. Okay? So you could write a function that basically fill this array one position at a time, and then once you fix the first position, you recurse to the next position, and so on. And then at the end, the base case of recursion, you take this number that's represented by the exponent vector and ask, is it between x and y? The way that you construct it, it should always be less than or equal to y. So then the question is at least x. And if so, you add it to your list of answers. And then at the end, you have this list of answers, either it's empty or not. You sort it so it's in increasing order, then you print it. Okay? I'm not going to show you the code because I wrote it in a completely different way. I actually solved the problem in a very different way. But here, I want to emphasize for this particular set, exhaustive search. And in this case, what I'm searching, it's actually the exponent vector. Now, the other thing that you have to, maybe I didn't really say explicitly, is that when you're searching for different exponent vectors, remember that every single different exponent vector will lead to a different number because of the uniqueness of prime factorization, right? So if you have, I don't know, 2 squares, 3 to the 4th, and then later on you have 2 to the 1, 3 to the 3, and 5 to the 2, these two numbers are guaranteed to be different. Okay, so you don't have to worry about generating 2 different vectors of exponents, and somehow when you add the numbers into the list of answers, you end up with duplicates. What you are not sure about is the order in which the numbers are regenerated as you explore this list of exponent vectors. But once you have the list of answers, you can just sort them. Okay, so basically this week, I guess the idea is that we are doing exhaustive search. And I want to show you 3 different kind of searches. So here we are. You can refer to my solutions. As I said, I did this problem in a very different way. If you want to look into my solutions, you can go into my GitHub and then look at it, and feel free to send me a message if you want to know why or how I'm doing that problem in a different way and why that works and so on. Okay. All right. So I'll see you guys again next week then. Bye.